Hello everyone, my name is Nicholas Garrett and this is my Physics Lab 5. So the purpose of this lab is to compare and contrast a visual model versus a computational model following Slinky and analyze the effects from its surroundings. And we will find that the Slinky is going to, at the bottom, will remain unmoving. And we're going to go into further more detail on why that is the case. But before we can do that, we have to go over some fundamental principles. So obviously, we're going to be starting off with our strong Newton's second law. The net external force equals the change in momentum of the system divided by the time. And here are some extra forces. We're going to take a note. Gravitational force and our drag force, which are going to be playing big roles in adjusting our net force and therefore our velocity. We're going to have the position update, which is important for our graphs to see the difference between the predicted versus the tracker. And we have FNet, of course, we went over that, and the velocity update formula. Quick side note, our system and surroundings. The system is going to be our Slinky, and the surroundings is going to be the Earth and air and everything that really interacts with the Slinky. Now, from the internet, I got some tracker values. I got the values of basically the object mass, which in this case is going to be our Slinky. Derek Miller, which was in the video, and I added his shoes by an offset a little bit from his height. Initial velocity starts at 0. We're just going to say that. Starts from rest. And then the initial position, which is something I got from rearranging around the grid. Okay, here's the little video. We can see that it's completely still at the bottom here, and then eventually when it catches up, kind of smacks it. It's done being stretched out, and it falls straight to the bottom. Now here is going to be for the predicted model our glow script. Now we have the ball, it's actually the spring. Spring mass, that value right there, delta t, we take note, gravity, and then our j hat, which is basically just saying where does y go. And right here we have our proportionality constant, which this is just fidgeting around with some values to find the correct one. And some slightly more interesting code, we have our loops 1 and 2, which, this loop is first going to execute before our second one. And this is basically saying, like, hey, tensor force is going to cancel out, our bottom should stay at the bottom where it is, and then eventually, once it's caught up, basically when it's done being stretched, gravity should take full force and just plop down. And we can see here we have retention, and then in the second one we mentioned drag and gravity. And so here's the graphs that these two produced. We have our tracker. We notice it's quite bumpy, and this could be due to human error and like unnecessary X component. And then our predicted model, which is quite straight, pretty linear. We notice that probably the predicted model is a little unrealistic. There's maybe some extra forces we're not taking into account here. I think there's going to be a lot of different motions that cannot just be described linearly. So we can say that the difference here is probably going to be a result of net forces we're not accounting for. Accurately, I mean. So furthermore, that could have thrown off some things and maybe not given us the results we wanted. We, of course, have the rounding errors, and we have unaccounted, net forces affecting our system. And it was quite tedious to place each and every center point mass or point mass at the bottom. So that could have made it a bit rougher. But we can see that they actually were relatively similar after the correct proportionality constant. Okay, and what did we learn from this? So the bottom stays stationary throughout most of the video. And it does this because the tension force of it wanting to compress back is canceling out with the gravity temporarily, leaving it to have the illusion that it's hovering over the air, but it's really just being compressed. It wants to compress because it's stretched. And that's why it does that, because while the force of gravity is obviously greater, but it's still being canceled out to a certain point where it is compressed to its relaxed length, its equilibrium length, and then it will proceed to fall down in its entirety. So what can we do to change the results of this? So we can actually, so obviously like a shorter spring, different elevation, you know, there's plenty of things that could affect this. Maybe a mass attached to the bottom. And that would maybe throw off the solution of it hovering.
Thanks for watching.